All right, let's get started with section 7.1, angles and their measure. So, we're going to take a look at some angles and some terminology to get started. So, a ray is, from geometry you'll remember, you start at a point and go forever in one direction, whereas a line goes in both directions forever. All right, so we have rays to make up an angle, and an angle is going to be formed by a ray for your initial side, and then we rotate that ray through angle, this is alpha, and end up on our terminal side. All right, so a couple of phrases there, alpha, initial side, terminal side. We're rotating counterclockwise, and if we're rotating counterclockwise, we're going to call that positive angles. Whereas if we rotate the other direction and end up in the exact same spot, if we're rotating clockwise, it's a negative angle. All right, we can also rotate more than a full circle, so if we spin a full circle and then go a little bit further, we would end up in the same spot, the same terminal side, be in the same location. It would be a counterclockwise positive rotation more than a full circle. All right, so we are in standard position if our initial side is on the x-axis pointing in the positive direction. All right, so we are in standard position and theta is positive because we're rotating counterclockwise. Here we're in standard position because our initial side is on the positive x-axis, but we're negative because we're rotating clockwise. All right, here theta lies in quadrant 2. Remember our quadrants, 1, 2, 3, and 4. And here we're in quadrant 4. So you'll see it's wherever the terminal side ends up is where we'll say our angle is. Here we're in between quadrants 3 and 4, so we're on the negative y-axis. We'll call this a quadrantal angle. All right, if our terminal side and the initial side are the same, we must have spun a full circle, exactly one circle. So one revolution counterclockwise, 360 degrees, positive 360 because we rotated in the positive direction. Okay, a nice right angle, quarter revolution, that's 90 degrees. And if we rotate a half circle, we end up with a line from positive x to negative x. All right, now that we've seen all of those, let's draw each of these angles. So 45-degree angle, we're going to draw all of these in standard position. So there's my initial side, there would be my terminal side. We draw 45 degrees, opening that direction. Negative 90, here's my initial side, here's my terminal side. We go down 90 degrees in the negative direction. 225, let's see where that would be. So we're going to rotate 90, 180, not quite 270, but another 45 degrees would get us out here to 225 degrees. And 405 degrees, let's start here. 90, 180, 270, 360. We need another 45 again to get us out here to 405 degrees. All right, try problem 11. Oh, I didn't realize they were going to draw them in for us. There they come. Look at that. All right, let's convert between decimals and degrees, minutes, seconds. These are some different forms for our angles. So, an entire degree can be broken up. Let's start over. A full circle can be broken up into 360 degrees. But each of those degrees can be split up even further. So a degree can be split up into 60 minutes. And a minute could even be broken up even further into 60 seconds. So you'll see the double tick mark is seconds and the single tick mark is minutes. All right, so how would we convert back and forth? Well, in this case, they tell us we have 45 degrees plus 10 minutes. 10 out of 60 degrees, plus 15 seconds. If there are 60 seconds in a minute and 60 minutes in a degree, 60 times 60 is 3,600 seconds in a degree. All right, so you plug those into your calculator, and it's going to spit out for you. Let's see what I've got here. I already punched this in. 45.1708 degrees. Okay, going back the other direction, we would say this is 21 degrees plus, let's figure out how many minutes this is. So we're going to go 60 times 0.256. and we end up with 15 point, let's see, I ended up with a decimal, but let's go ahead and plug it in. Where's our calculator? So in this problem, we're going to go 60 times 0.256, and we get 15.36. Okay, so 15 minutes, but then we have this 36 hanging out there. So how about 0.36 times 60 again to figure out how many seconds there are. And there's 21. So we would have 21 degrees, 15 minutes, 21.6 seconds. All right, try problems 23 and 29. All right, so we've always dealt so far in degrees, like 90 degrees would be a nice right angle. But we also have another unit, just like there's Fahrenheit and Celsius for temperature. There are radians, which is another unit of measurement for angles. All right, and so we'll talk about the definition in a second. But before we do, let's use them to find an arc length of a circle. All right, so the arc length is the distance along the edge of a circle. And we're going to call that S. S is the arc length. Distance along the edge of the circle. All right, and so the way you do it is you use ratios. The ratio of one internal angle, theta, to another one, theta 1, is going to be the same as the ratio between S and S1. And we have a formula here called, for the arc length, S equals R theta. Now theta needs to be in radians. All right, so theta's in radians. So S equals R theta. Find the length of the arc of a circle. So we're trying to find S. The radius is 4. The central angle is 0.5 radians. So we're just plugging them in. S is going to be 2 meters. All right, try problem 71 using that formula. Okay, so let's talk about converting from degrees to radians. Here's the key. One full circle, 360 degrees, is 2 pi radians. That's the definition. All right, so if we split that in half, 180 is pi radians. So we can have these nice fractions. 1 degree is pi over 180 radians, or 1 radian is 180 over pi. And what you want to think about if we're converting is we want to cancel out our units. So if I have 80 degrees, I want to make sure 80 and 180 are on, one's on the top and one's on the bottom, because we'll have degrees that will cancel out. So if I put 180 degrees on the bottom, I need to put pi on the top so that we stay consistent. We can cancel our degrees. We can cancel a 0 even. 8 goes into 18 how many times? Divide them both by 2. You get 4 pi ninths. How about 140? 140 pi over 180. Cancel your degrees and your 0. 14 over 8. We can get 7 pi over 9. How about negative 30? We could say pi over 180. Oops, not the pi. I want to keep those. Negative 3 into 18 is going to be negative pi over 6. And lastly, 100. Pi over 180. 10 over 18 divided by 2, 5 pi over 9. All right, try problems 35 and 61. Let's go the other direction. Let's convert back into degrees. So 2 pi over 3. We need a pi in the denominator so we can cancel it out. We need 180 degrees in the numerator. Cancel, cancel. 180 divided by 3 is 60 times 2 is 120 degrees. How about 5 pi over 6 times 180 over pi. Cancel your pi's. 180 over 6 is 30 times 5 is 150. Negative 3 pi over 5. 180 over pi with the degrees. Cancel, cancel. And 180 over 5 is going to be, what do we have here? What is 180 divided by 5? Drawing a blank. 36, there it is. 36 times 3 is going to be 90, 108 degrees. All right, and we could keep going, but let's go ahead and try problem 47. I think you get the idea. Okay, so here's a nice little chart here of the common angles. So I would recommend writing this down in your notes. You're going to want to use these angles a lot, so you can pause the video and get these down. Okay, so let's try to figure out a problem like this. The latitude of location L is the angle formed by a ray drawn from the center of the Earth to the equator and a ray drawn from the center of the Earth to L. Alright, so we can see it here. If I want to find the latitude, I figure out what the angle would be from an initial side on the equator to the terminal side going straight to my location. Alright, Glasgow, Montana, not Scotland, Montana, is due north of Albuquerque, New Mexico. Glasgow's at 48.9 and Albuquerque's at 35.5. So what we want to do is figure out the distance between them. So this is going to be, let's see here, 48.9 and 35.5. If we subtracted them, we'd get 13 degrees 4 minutes. All right. We also know the radius is going to be 3960. We want to find this distance here. And since it's on a circle, right, we're going to assume that slice of the Earth is a circle. We can use our formula, S equals r theta. So we're trying to solve for S equals the radius is 3960 and theta is 13 degrees 4 minutes, but we need to turn this into radians. Alright, so first we need to figure out that minute part. So we're going to say, let's grab our calculator, 4 over 60 is 0.06 repeating, plus the 13. So that's how many degrees we have. We need to turn this into radians, so let's times it by pi over 180. Alright, so that's how many radians we have. Let's times it by 3960, the radius. Don't confuse radius with radians. And we get 903 miles is the distance between Glasgow, what was it, Montana, and Albuquerque, New Mexico. Alright, try problem 101. Okay, let's find the area of a sector of a circle. We have a nice formula for this. The area is 1/2 r squared theta. That should be pretty similar because the area of a full circle is 1/2 r squared times pi, right? Pi r squared theta, pi r squared over 2. We've known that one for a while. So we're going to replace pi with theta. Alright, so let's try this. Find the area of a sector of a circle with a radius of 5 formed by an angle of 40 degrees. Area equals 1/2 5 squared. Don't just put 40. Convert it into radians. Got to be in radians here. Alright, so if we plug this in, we're going to end up with an area of 8.73. And our unit would be square feet. Try problem 79. Okay, last objective. Find the linear speed of an object traveling in circular motion. So, remember that speed is distance divided by time. So the distance would be the distance you travel along this edge, which is s divided by time. Alright, angular speed is how much angle you travel divided by time. And we're going to use omega. Alright, so if we put those together, v equals r omega, you get that from saying v equals, remember s, the formula for that is r theta over t. And if we say theta over t, look at that, we've got that right there. So by substitution, we get velocity equals r omega. Don't say w. Okay, don't say funny 0. We've got theta and we've got omega. Alright, so let's use some formulas here. Now you can use any of these to figure this out. So the distance from the axis to a location on Earth 40 degrees north latitude is about 33.5. Alright, so we don't have a perfect radius. The Earth is actually not a perfect sphere. It's kind of skinnier at the poles than it is at the equator. So we have a radius. We want the linear speed, so we want v, on the surface of the Earth at 40 degrees north latitude. Okay, so since I have a radius, I'm going to use one of these formulas that uses the radius. So how about this one? V equals r theta over t. Again, I could use any of those forms. So I have a radius, 33.5. What about a theta and a t? So we want to think, okay, how long would it take us to make some movement here on the Earth? And so I think we know that we would go one full circle in 1 day. So how about 2 pi, because that's a full circle, over 24 hours. And since this is in miles, we'd end up with miles per hour. So let's go ahead and plug that into our calculator. 33.5 times 2 pi divided by 24, and we get 794 miles per hour. All right, try problem 97 and you are all set. Any questions, make sure we're asking them in class. Good luck with those problems.